So, hello everyone. So, we are going to start the new lecture today, that is extraction and chromatography. So, basically this is the first step of isolation after separating the cells in the case of extracellular product and after cell disruption in the case of intracellular product. So, in the last lecture we discussed the summary of different methods used for the cell separation and cell disruption, and in the case of cell disruption we discuss in detail about mechanical as well as non-mechanical methods. So, mechanical method they apply different shear stress, impact and forces. In the case of non-mechanical method we apply the chemicals, it may be enzymes as well as the osmotic pressure. So, in today's lecture first we will be discussing with what is aqueous two phase liquid extraction, then we will see what is typical liquid extraction, then we will go to the next topic, that is chromatography and what are different type of chromatography. So, extraction, what is extraction? It's as the name suggests, it is a process of separating desired substance from the mixture. And how it is done? It is used to isolate the target product from the complex mixture, and it involves liquid extraction, solid liquid extraction or other separation techniques. So, typically when there is a liquid extraction we refer as solvent extraction, and when there is a solid liquid extraction we refer as a leaching. So, one simple example for solid liquid extraction is you are having the hot water, you put the tea. What will happen? The tea will leach out from the solid to the liquid phase. Now, once you are having soluble products, so you need to separate those soluble products. So, the separation principle is the mass transfer, and we will see how this ideal stage concept works. So, as I told, the extraction is a primary isolation of the product by a mass transfer between phases, and mostly those phases will be immiscible. So, what are the different setups? One can have the mixer settler or extraction columns. So, you just see this is a mixer and this is a settler. So, in the mixer you are having two immiscible liquids Li1 and Li2 with the solute concentration CaI1 and CaI2, they are mixed and then they are allowed to settle, and once they are settling then the outlet streams are LO1 and LO2 with concentration of CaO1 and CaO2. And what is happening? The solute A transfers until it reaches the equilibrium between two immiscible liquids. What is the driving force here? The driving force is the delta C concentration difference, because the concentration of A in one phase will be higher as compared to the other phase. So, that is why it will transfer from the higher concentration to the lower concentration. So, ideal state, what does it mean? Ideal state says at the outlet CaO1 and CaO2 are equilibrium concentration, and once they are equilibrium means they have achieved the maximum efficiency and no further mass transfer possible. But in the real case what happens, in each stage only partial equilibrium is approached. So, we require the multi-stage extraction. So, one can calculate what will be the stage efficiency. It can be calculated as change in the concentration achieved in the real stage divided by change in the concentration in ideal stage. So, we will see there are a lot of scope for this aqueous two phase liquid extraction. So, the only requirement is this solute, it should dissolve in the other immiscible liquid what you are adding. So, what will happen? It will try to move from one liquid to the another immiscible solvent. So, example, you can extraction of penicillin, there are many solvents like butyl acetate, amyl acetate. Extraction of erythromycin, there is a amyl acetate, pentyl acetate, and recovery of steroids, vitamin B12, alkaloids. So, how it works? At the laboratory scale, we use separating funnels. So, it has a simple setup for a small scale product recovery. So, what you do? First, you have to do the mixing to maximize the mass transfer. Then, you have to allow to settle, or you can say the phase separation. Then, you can remove the heavy phase and light phase. So, the light phase will be at the top, heavy phase will be at the bottom. Industrial relevance, the organic solvent widely used for antibiotics, but again if your product is sensitive to those solvents, let us say protein or other sensible products, so this method cannot be used. Then you have to go for the other adsorption or this chromatographic methods. Aqueous two phase extraction uses, let us say, polymer salts in the water, then it forms the two immiscible phases. So, it is a gentle methods, and depending on the solvent it can produce enzymes, recombinant proteins, or even cell organelles. And differential partitioning depends on the molecular size, charge, hydrophobicity and affinity among these two liquids. So, there comes the term of partitioning coefficient, how it is going to preferably choose one solvent over other. So, it says, let us say K partitioning coefficient is the ratio of equilibrium concentration in the upper phase. Let us say concentration in the upper phase is CaU and concentration in the lower phase is Cal of A. So, A is now distributed into upper phase and lower phase. So, if the value of K is greater than 1, then solute favors the upper phase, and if K is less than 1, the solute favors the lower phase. And typically when we go for the single stage extraction of enzyme, the partitioning coefficient greater than equals to 3 are normally required. Now, we assume this let us say total volume was initially V naught and now it is distributed as Vu upper phase plus Vl lower phase. So, we can calculate the yield of solute in the upper phase. You can calculate YAU. So, what is the volume in the upper phase? Vu. What is the concentration in the upper phase? CaU divided by what was total volume initially, Vo, and let us say concentration was corresponding CaO. Now, Vo and CaO, it can be written as V naught O into Ca naught equals to Vu CaU plus Vl Cal. So, it can be written as Vu CaU divided by Vu CaU plus Vl Cal. Now, we already know partitioning coefficient is defined as CaU upon Cal. So, this can be written as Vu divided by Vu plus Vl upon K, and it can be further simplified if you take the ratio of volume of upper phase and lower phase. So, it will be VU upon VL divided by VU upon VL plus 1 upon K. So, in this way we calculate the yield absolute in the upper phase. In a similar manner, it can be calculated the yield absolute in the lower phase. So, this will be finally YAL will be VL upon VUK plus VL. So, we will see what is the effect of this VU upon VL ratio. So, there are some examples here like polyethylene glycol and salt mixture. So, debris partitions to the lower phase and target proteins they are recovered in the upper phase. What are the operation characteristics? The equilibriums are rarely reached, they are only approached. So, one need to go for multi stages, and mixing increases the surface area for transfer. So, it results in a faster mass transfer, but there is still challenge of the phase separation due to low interfacial tension among two different phases. To achieve that, one option is one can apply the centrifugal separator for the rapid large scale extraction. In that case, the recovery up to 90% is achievable in a single stage, and if this recovery is insufficient, then one can use multi-stage extractions. So, we will just see one example here. It says aqueous two-phase extraction is used to recover alpha amylase from solution, and for this a polyethylene glycol and dextran mixture is added, and the solution separates into two immiscible phases. The partitioning coefficient of alpha amylase is K equals to 4.2. Now, we need to calculate the maximum possible recovery percentage when there are two ratio are given. Ratio of upper to lower phase is 5 and volume ratio of upper to lower phase is 0.5. So, if you remember the formula, we discuss YAU as we have written in terms of ratio also, it was VU upon VL divided by VU upon VL plus 1 upon K. So, in the first case the ratio is 5 divided by 5 plus 1 upon K, K is 4.2. So, we will be getting this recovery close to 95.5%. And if you do the same calculation with the ratio of 0.5 here, so this will be YAU, this will be 0.5 divided by 0.5 plus 1 upon 4.2, 1 upon K, and this results in a 67.7%. So, what it says, you need to use more solvent to achieve a better extraction efficiency. Now, we can see in particularly in downstream processing, this application of liquid extraction, it used to separate the inhibitory products like ethanol, acetone and butanol. It is used to recover antibiotics. It is separation is based on the solubility difference of solute in immiscible phases, and the choice of solvent or extractant depends on certain property like non-toxic, selective, inexpensive, immiscible with broth and high distribution coefficient or high partitioning coefficient. We just see the liquid extraction, which we refer in downstream processing. It is also referred as solvent extraction. So, it says the separation of constituents of a liquid solution by contact with another immersible liquids or solvent. So, once you mix it, and then depending on the partitioning coefficient, it try to distribute among two immiscible liquids, and this separation can be enhanced by the use of multiple contacts. So, here when we say solvent extraction, so we are going to use different terms. We use the feed, F represent to the feed and S represent to the solvent. And now after the extraction you are going to get two phases, one is called raffinate and other is called extract E. So, feed is the liquid from which you want to extract your desired compound. Liquid which is added are the solvent in which you want to extract your product. Now, we are going to get two phases, one is the solvent rich product of the operation is called the extract, and this residual liquid from which the solute has been removed is called the raffinate. So, basically you just see we are using the Y here. So, it is rich in your product and XF is the remaining liquid, that is we are referring the raffinate, or you can say the lean phase. So, extract is the main desired phase or the rich phase. Similarly, the concentration here was XF, the concentration YS, this is X and this is Y. So, here we define distribution coefficient as Y upon X, K is defined as Y upon X, where Y is the mass fraction of solute in the extract phase at equilibrium and X is the same in the raffinate phase. Now, if you do the overall mass balance, what is inlet F plus S, this equals to R raffinate plus extract. We can write in terms of composition. So, this will be F into XF plus S into YS, this equals to R into X plus E into Y. So, from here we can write Y as F XF plus S YS divided by E plus R upon K. So, how it is coming out to be? What we are doing? We are replacing here X as Y upon K. So, this becomes R Y upon K and this becomes EY. So, if you take Y common, we will be having E plus R upon K. Further, if you are having the pure solvent means it does not have any solute at this moment, it means YS is 0. So, this only becomes FXF upon FXF upon E plus R upon K. Now, many times what happens? Of course, there will be change in the composition, but there is not significant change in the amount. So, we assume that F equals to R and S equals to E. So, here in place of FXF one can write Rxf. So, if I write here in place of Fxf, one can write this Rxf, and this term for the pure solvent is turning out to be 0. So, now what will happen? You can bring down this R in the denominator. So, and K will go to the numerator. So, we will be getting K into Xf divided by R divided by R will be 1 plus K E upon R. So, it says Y is inversely proportional to 1 upon ratio of E to R. So, it says a decrease of E to R increases Y, but at the same time if you just see the recoverability, which is defined as E into Y upon R into Xf, what is recovered in the extract and what was initially there in the feed. So, it can be again rearranged in terms of E and R. So, we will end up with K into ER divided by 1 plus K into ER. So, it says recoverability is directly proportional to E upon R. So, if you decrease the E upon R, at the same time it will decrease the recoverability. So, what it says, therefore, an optimum operation condition has to be determined to balance between the recovery Y as well as the recoverability. You have to balance between the Y and gamma. Now, we can have the multi-stage extraction, and that can be operated in different modes, like in the case of counter current extraction. So, here your feed is entering from here and your solvent is entering in a reverse manner. So, you are having NP stages 1, 2, 3 and so on and so forth. So, what is entering here is the F, what is entering here is the S, what is going out is the RNP, and what is going out here is the E1, extract 1 and RNP. You can also have the cross current, it means you are feeding the solvent in the different stages and feed is passing, this will be the feed. So, here the feed will be R1, here the feed will be R2 and so on so forth. So, we will just see how we can calculate the number of stages required for the extraction. So, we just will do the simple mass balance for one case, that is the counter current extraction. So, you just see it will be F plus S, F is in, S is in, this equals to the E1 is going out, and what is going out here is the RNP, RNP. In terms of concentration, it can be written as F XF plus S YS, this equals to E1 Y1 plus RNP or XNP. Now, at equilibrium, what we will see is you can just rearrange Y1 and it will come out to be R upon E XF minus XNP plus YS. So, here again we are assuming this F equals to R and S equals to E. So, if this is the case, this can be generalized for n number of stages, because Y1 means we can write yn plus 1 equals Ys. Where is the Ys is there? This is coming at the last stage or one stage. So, we can write Y1 minus R upon E, rather we are writing Ys here. Ys is Yn plus 1, this equals to Y1 minus R upon E xf minus xn. So, in this way you should be able to calculate the yn for n number of stages. Now, how we will decide this, how many stages will be there? So, what should be the value of yn? Yn plus 1, its value should be always less than or equals to the what was the concentration in the solvent. It cannot exceed the concentration in the solvent. So, there we have to stop the iteration and one can count how many number of stages will be required. So, you just see this, this is the x versus y graph. So, you are having equilibrium line that corresponds to y equal to k into x, and you are having operating line, the slope is r upon e, and you are starting with the y1 because you are decreasing y1 minus, you are starting with the y1. So, stage 1 we reach to this value of y, stage 2 we reach to this value of y, stage 2, stage 3, and you have to count the stage till you reach the y1 value is greater than, is less than or equals to the ys. So, there here you can see 1, 2, 3, 4 stages will be required. So, in this way we can calculate how many stages will be required for the extraction. Now, next is the chromatography, because as we discussed in all the cases you cannot use the solvents depending on the nature of your products. So, for that the other technique is separating based on the differential affinity, and the role of chromatography is to purify the extracted product to a high degree. So, it separates the component based on their interaction with stationary and mobile phase. So, in the chromatography involves the mobile and stationary phase, and mobile phase is the solution containing the solute to be separated, and elutant that carries the solution through stationary phase. Now, this mobile phase composed of several solutes is injected at one end of the column, and each solute in original solution move at a rate, this is important, which is proportional to its the relative affinity. So, rate is proportional to its affinity for stationary phase and comes out at the end of column at a separate time, and we get the distinct bands. Now, stationary phase, it can be adsorbent, it can be ion exchange reagent, it can be porous solid, or it can be gel. Now, the separation of solute is based on the different interactions with stationary phase, and mobile phase, which is elutant, it carries the solute. And so, what happens? The weakly bound solute will elute first, and strongly bound solute will elute in a different time intervals at a later stage. So, output, what is the output of the chromatography? It appears as a separate peak at different retention time, and that retention time depends depending on the what is their specific relative affinity towards the stationary phase. So, you just see how this differential migration is achieved here. You are adding the feed first, then you are passing the mobile phase, you are referring as a elutant. So, what is happening in the feed? Both were at the same time, but when they are flowing they have different affinity for the stationary phase. So, with the time we just see first B will come out, then A will come out. So, it means A has more affinity in this case. So, we can also calculate the capacity factor of a column, which is defined as K as VE volume of the eluting solvent minus VO, void volume of the column, because this solvent can also go into those void volume, divided by V naught. It says what is the capacity factor of the column, and when you are using, let us say, 2 solute, then you need to calculate the selectivity or relative retention, and it is defined as K2 upon K1, and K1 K2 are the capacity factor of for the 2 solutes. So, it says K2 upon K1. In this way one can calculate the selectivity or retention for 2 different solutes. So, you just see here you have loaded your samples, and you just see as they process away, here you are having mixture of, let us say, 3 distinct compounds, and at the end you just see all 3 are separated, and corresponding you are getting 1 peak here, 1 peak here, and 1 peak here. So, how it works? First you have to inject into the column, then you pass the elutant or mobile phase, then the solutes travel at different rate and separation is achieved, and output is this is the chromatogram. Here you will see the different peaks. So, typically what happens, the mobile phase, it is a fluid that moves through the column, or is also referred as elutant, and stationary phase is the material inside the column. It may be resin or solid support that is responsible for the separation. So, we can use there are special methods like elution chromatography. The solutes are separated while being diluted. One can also have the fixed bed adsorption, when solutes are adsorbed first, then eluted separately, and it may be sometime we say this kind of a desorption. Or you can also have the displacement. You are having the displacer with the more affinity, so that will push the solute and forms the concentration zones. So, you can see there can be ion exchange or affinity chromatography, there can be gel filtration, it can be affinity chromatography, or there can be HPLC. So, it all depends on what is the nature of your solid phase. And column operations, this material or stationary phase is packed, and then solutes is passed through it, and it forms, once it goes out, it forms the different bands, and there is certain assumptions like a rapid equilibrium between solute and adsorbent, and negligible radial gradients. Now, depending on this solid matrix, we can have if it has the affinity with solute through adsorption, like silica or alumina, they have weak van der Waal or steric forces on solids, they are called adsorption chromatography. There is a liquid-liquid partition chromatography, when separation is by different solubility or partitioning coefficient between 2 immiscible phases, and if the separation is based on the ionic charge or electrostatic interaction, that is called ion exchange regime. So, in the case of ion exchange regime, what will happen? First you have to load your solute, then you have to change your elutants or buffer in such a way that it breaks that, or it loses out those electrostatic interaction, then you are going to elute separately. Then gel filtration, or also known as size exclusion chromatography, it is based on the molecular size and the shape. So, typically the small molecules enter into the pores of your packing material, and then they will take longer time to come out of the column. Next is the affinity chromatography. They are highly selective, they may have a specific binding group on the surface, like enzyme substrate binding, antigen antibody binding. Hydrophobic chromatography, this separation by the hydrophobic interactions. In adsorption, we consider the weak van der Waals forces. Here we are considering the hydrophobic interaction. And HPLC, it is quite commonly used at both lab scale and as well as at the large scale. So, it uses the high pressure. So, this includes high liquid flow rate, and it also consists dense column packing, and it results because of the high pressure, fast and high resolution. So, this is quite commonly applied for the separation. So, here you just see how it works, particularly in case of affinity. This is solid matrix, it is having a ligand, and ligand, let us say you are having 3 different type of solutes. So, it is specific to this, it will bind to it, and then further you have to elute this, that is it. While the other two, they will quickly pass through the column. In the case of gel filtration, this is based on the size exclusion chromatography. So, here let us say you consider what is the total volume of the gel. It is the sum of void volume plus Vi is the internal volume of liquid within the pore of particle plus Vs is the volume of the gel. So, it says total volume will be void volume plus internal volume plus volume of the solid or the volume of the gel, and there this partitioning happens based on the partition coefficient Kp, which is defined as Ve minus V naught upon Vi. So, we can write volume of elution is equals to Kp to Vi plus V naught. So, this is the volume of elutant will be required, and what is the Vi? The internal volume of liquid within the pore, it is property of materials. So, here A Vi is A into Wr, and A is the mass of dry gel and Wr is the water regain value, which is defined as volume of water taken per mass of the dry gel. So, this volume and mass, it can be also calculated in terms of respective density. So, rho g is the density of the wet gel and rho w is the density of the water. So, it says you can quickly calculate the Vi from the given fluid property. Kp is gel partitioning coefficient, Vo. So, one can quickly calculate what should be the Ve or the elution volume. So, total elutant volume will be Vo plus Kd plus Vi. So, typically we can rearrange this equation in such a way that V upon Vo will be 1 plus Kd Vi upon Vo. So, to calculate the molecular weight, what you have to do, you can plot V upon Vo versus different molecular weight solutes, and typically it results in the straight line. Then you run your own sample, and from there you can easily estimate what is the molecular weight or the size of your molecule. Now, next there are two terms in this chromatography, that is yield and the purity. The yield is defined as amount of solute I eluted divided by what was the total amount of solute. So, how do you know what is the total amount of solute? If you integrate from 0 to infinity, Yi is the solute concentration, F is the solvent flow rate into dt. If you integrate for infinite, you will get total amount of solute, and if you integrate for the 2 time range T1 to T2, you will get amount of I eluted. In this way, we can calculate what is the yield of solute, and also at the same time it is important to calculate the purity. So, purity in the same given window delta T, T1 to T2, it will be the amount of solute eluted divided by amount of impurity eluted. So, let us say I is your solute and J is your solvent. So, for the given time how much yi f into dt you got and how much you got for the impurity. That suggests what is the purity of your solvent and what is the yield. Yield is for the given time T1 to T2 divided by T1 to the you can say 0 to infinite. So, you can get what is the maximum amount of solute. Now, we can quickly compare these two methods what we discussed today, that is extraction and chromatography. So, typically extraction is the initial separation step and it is based on the solubility as the phase partitioning, and it is cost effective, but at the same time it is less selective. Chromatography, it is a high resolution purification method and based on the molecular interaction with the stationary phase, and it is a more complex and relatively expensive. These are the common applications for these methods, like separation of proteins and antibodies, purification of vaccines, extraction of natural compounds from the plants, and also for the quality control in the pharmaceutical manufacturing, you need to quickly monitor the quality of your product. So, with this I will stop here. So, today we discussed the first step of isolation, that is the solvent extraction, and also we discussed the chromatographic methods. Thank you so much.